And I'm actually just testing the audio here on the live stream. Are you able to hear me now? I actually just talked in the live stream. Do we have audio in the live stream? Are you guys able to hear me? Actually, John, are you here? John, are you logged into the live stream? Hello? Are you guys still there? Are we good? Actually, if you are already on this YouTube live stream and you're also in the Zoom call, could you please unmute your mic and just say that you can hear me? Because that helps me know that I'm through. Excellent. Okay, so this is going to have a round trip delay of maybe about 2 seconds, because that's how long it takes for the signal to get to YouTube and back around. And I'll keep setting up these different devices. So we're here. Okay. Oh yeah. We want that to be muted. Yeah, you will not be getting audio from me directly into the Zoom. So I will actually not be making any audio in the Zoom. In fact, I'm not recording any audio in the Zoom, I believe. At least I hope not. Okay. Instead, I like to see everybody. Is there a gallery view that lets me look at everybody who's in the Zoom or not? Oh, I don't want to share screen. Anyone having trouble accessing live chat? Yeah, so just to let you guys know, and John, I hope you're still hearing this live stream, because that's the way I'm communicating with audio right now. And so if you can hear this live stream, we'll be doing all of the audio through the YouTube. We will not be doing any of the audio through the Zoom. But John, is there a way for me to go and see everybody on this call? Right now, I only see the general screen. Will I be able to see everyone on this call later when it's time? Now turn that sound on. So this is a sound test on the YouTube. It's starting in 1140s, 1139, 8, 7, and so on. If you happen to be, I should actually mute this, yes. If you happen to be in the Zoom call, I just would like to make sure that you're able to hear my audio now, because now all of the audio is running straight through the YouTube. Are we good? We're good? Okay, I'm going to now check the video. Here we are. So now actually the video is coming through on the YouTube hopefully as well. Hi, this says hi, because this particular video stream that you have here on the Zoom, I guess, we can keep it there just so that we have this, but now you're going to be seeing me from the side, because what's actually happening here is that it's being recorded in front. I don't know if you can see what's going on here. I don't know if I can even see what's going on here, but there's something in front. Yeah, those are the two screens, and there's also a camera. And so that's actually what's sending all of the output into YouTube Live. And so the video stream that you happen to have here on the Zoom is not essential. Actually, this one, there will be no audio with it. So the way to follow this would just be to keep watching the YouTube Live. But at the same time, I put the display up right in front. So when I'm looking this way, I actually can see all of you guys waving and so on. So can we test one more thing? Would you be willing to raise a hand? Just like there's a raise hand, you could either try to wave, but there are so many people on the call that if you press the yellow thing, I think there's some way to raise hand in Zoom. I'll try to be paying attention, so if I see someone raising a hand, I'll try to call. But could you try testing the hand raise feature in Zoom? Have you used that one before? Yes, I see. So this is Nicole Sullivan. Is that you? Oh, that was a thumbs up. But in any case, I can see something. And so next thing I want to test is would somebody be willing to try to say something just so that I'm able to hear this? Could you raise your hand? I'll call on you. I want to see if I can hear through this side when you say something. So somebody please raise your hand, and I'll just call on you. You can either raise hand this way, or you can raise hand with the yellow thing. Because I want to make sure that when you talk, I can hear the sound come through on my side. Is someone willing to help me volunteer to test whether or not you can make sound and I can hear? Yes, Jillian, I'm having trouble reading that. Jillian Winters, could you please try unmuting your mic and then saying something, and I'll calibrate this volume. Okay, so that means everyone else can hear you except me, which is a problem. Okay, let me adjust this. Same as system, that should be right. That's what happened. Here we go.
We can hear you.
Yes, and so can I too. So there we are.
But our professor can. Okay.
I can. I got you now. So basically, I should say these Windows computers get me very confused. I personally don't use Windows, but somehow this particular Windows computer has so many different sound devices that it was playing out of the wrong one. Sometimes you'll see my hand come across here. That's only because I'm adjusting the volume in real time, because I don't want to blast the volume around. One request I'd make is that because of the fact that this is playing through YouTube Live and also in general playing through speakers, the echo cancellation of the sound doesn't work so well. So for example, if you wanted to answer a question, it'd be best if you either had headset, or if while you're answering the question you temporarily mute your speaker, or else you'll get like some back and forth sound. We'll figure it out as we go. Okay, yeah, but thank you for helping me test. I can definitely hear you now. And I'm going to try to run this thing as interactively as I can.
Just so everyone knows, I lowered everyone's hand.
Oh, that's what happened. So you lowered everyone's hands. That's good. And again, there will be this apparent delay in how this class is going of about 2 seconds, just because that's the amount of time it takes for me to upload the video to YouTube and YouTube to send it around. Elisa, how are you? Is that a wave or is that a hands up? It's a wave. Looks like a wave. Okay, wonderful, wonderful. Yeah, so we'll be doing it this way. I'm actually still going to get a few more items. I just wanted to double check that the whole system worked. So I'm going to bring over some notes that I may or may not use as we keep going. Meanwhile, I'm going to switch. You know what? Yeah, I'll switch this. I'll switch the YouTube to the countdown just because in case anyone else is showing up, they will see that this thing is starting soon. But I will be back. I'll be back very shortly. It sounds to me like all of the system does work. Hello, everybody. It's a real pleasure to be here and to have a chance to talk to everybody on this evening. Actually, it's a real honor to be able to talk to so many mathematics teachers. To me, everyone here in this session, in this call, is extremely experienced. And in some sense, every single time that I run one of these sessions for teachers, I'll be honest, I get really nervous because I'll say that all of you, the combined experience that's in this Zoom meeting room or watching on this YouTube right now is enormous. I will also say, whenever I think about what I should do to give a session for teachers, it's very hard because you've also seen just about everything. So what I end up deciding to do is I end up deciding to talk about something which I myself didn't completely know the answer to. I mean, I like to use all of these sessions that I do with Math for America to learn something myself. Actually, oftentimes, the way I run these sessions is I ask Math for America, what kind of topic would teachers be interested in having? I'm just going to drop that microphone sound a bit. I'm always curious, what kind of topic would the teachers be interested in having? And oftentimes what comes back is the kind of question that I'm also curious about myself. And so here, this happens to be about matrices. I wanted to talk about matrices today. But at the same time, most of the people who are on this call have taught about matrices for many, 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 many classes. And so what could there be that's any different from what you've done? I decided to maybe think about what I was curious about and maybe dive in deep to even wonder why we do what we do with matrices. And I decided to make that the core of the very first session that I wanted to build today. I do want to say, if anyone is listening to this on YouTube who's not in the Math for America session, you'll notice that I'm going to do a lot of interaction with Math for America teachers. That's in the separate channel that we happen to have because this is primarily for the Math for America audience. But anyone else who wanted to join is, of course, welcome to watch. Okay. So let's go ahead. And also, since I just said that, on the Math for America group, if anyone has something that they would like to interject or say, I'm not entirely sure the best way to do this with Zoom, and that's why I'm glad that John is here. I'm not sure how long John will be here from MFA, but the problem with Zoom I'm having right now is I cannot see everybody's face on the Zoom at the same time. In fact, it says screen 1 of 9. And as far as I understand, I don't have a way to figure out who's raising their hand if it's outside of screen 1. So what I'd like to request is, John, will you be here for the whole entirety of the course, and if of this session, or not? I can actually hear you if you just answer.
I am.
You are. That's great. Then what I'd like to request is, John, if you see that there are people who are raising their hands, if you don't mind raising your hand with the yellow flag to raise hand or even to wave at me, then I would actually stop and I'd say, hey, John, could you help put somebody on who has something to say? Because I actually have a very hard time teaching if I have no feedback. So I want to encourage back and forth throughout here. In fact, I'm going to ask a whole lot of questions. Good? Okay. Great.
Yeah, I can do that. So usually, in live streams in the past, I've also people can store their questions in the chat window, and I can always go through them one by one and times work for you. Does that work?
So I understand that you said that there can also be things in the chat. Actually, that does work because I put the screen right in front of me, so I can also see that it says hello to everyone. The only problem is I wear glasses, and so my vision isn't that great, so I can't see who said hello to everyone. But I can see somebody ask things like, how do you raise your hand? So I will say, if I see things pop up in that chat window, I will also attempt to respond to those. I just have to apologize. Sometimes you'll notice me kind of squinting to try to see if I can understand what that was. Great. Yes, and the question is, do you just watch video and then use this to ask questions? Yes, so the way that I wanted to do this particular session is I want to do something where I can have a screen share, where I can draw. It's actually going to appear behind me. But the way that this works, somehow at least when I did this with my Carnegie Mellon students, the feedback they gave was that the quality of the video was higher. If it does turn out that it's worse this way than just running everything through Zoom, I'm happy to adjust for the next time we do this. But so the way I wanted to run this was that you just keep the YouTube live window open. That will be this particular stream. All the audio and video come through that. Whenever you have a question that you want to ask or some comment you want to make, switch over to the Zoom screen, either raise your hand and maybe get MFA's attention, or type something into the chat. I'll try to see it. And there's about a 2-second delay between when I say something and when it goes out through the internet. But apart from that, we'll work around it. Okay. So I guess that's the setup for what we're going to do today. And let's go ahead and start. So Matrices. Whenever I think about matrices, I remember when I was a student learning matrices, and my first big question was, who invented this way of multiplying matrices? Because what I remember is whenever I was learning this, I said, why can't we just make the matrix multiplication something much simpler? I mean, why couldn't we just make it so that if we're going to multiply a matrix like 1, 2, 3, 4, and multiply that by something like 4, 3, 2, 1, I remember thinking, I think this is probably quite common. High school students will wonder, why can't we just define matrix multiplication this way, where you just multiply entry by entry? And I think the first answer to that question is, in math, you're allowed to define anything you want. But unfortunately, it's only valuable if it's useful. So the question is this a useful definition or not? And it turns out it's not as useful as the definition that we use today. But I wanted to maybe motivate. And in fact, the first session I wanted to do here in this course was to motivate why we have this strange way of multiplying matrices. And that starts with the idea of linear functions. So with linear functions, I'm curious, what comes to mind? Oh, I see some people are asking things like, can anyone hear anything yet? Has the video started? I will say, if people are coming in a little bit later, it would be very helpful if we can maybe have John putting into the stream the link. Yes, the live stream link. That would be very helpful. Great. And I apologize for people who came in later. There's this additional piece. You need to go into the YouTube link. Okay. Let's keep going. Although that's a little bit odd for me to say that to the people who aren't in the YouTube link. I guess that doesn't make mathematical sense. But let me go back to the linear functions. If I say linear function, what comes to mind? I'm curious. Feel free to type into the chat or to raise your hand. If you raise your hand, I can also, well, if you happen to be on screen one, I happen to be able to see you. What do you think of when you think of a linear function? Yes, I see already. I see a lot of things that come up when we think of linear functions are things like y equals mx plus b. We think of things like ax plus by equal to c. And these are all exactly what we would learn when we think of linear functions. We think of a line. We think of constant rate of change. We think of things like this. We draw axes. We draw a line. And the answer is yes, all of these are linear functions as we usually use them. Except that for the purpose of this particular topic of matrices, we want to make a slight change to what we usually think of as the word linear function. And this is something I also didn't encounter until I started to see a linear algebra subject. So we can actually distinguish between this kind of line and another kind of line. Another kind of line happens to go through the origin. So these functions are not exactly y equals mx plus b. These, as you know, these are y equals mx. And these might be of the form ax plus by equals 0. So these functions are a little bit more special. And in fact, I want to focus on those. In fact, I'm going to call these linear functions. So these on the right we'll call linear functions. And another word that you can use to describe these functions is actually a little bit different. I see that somebody has mentioned about proportion versus linear. Yes, indeed, linear functions do represent proportion in some sense, because as you go further to the right, the amount that you go up is proportional to how far you've gone to the right. But yes, that's right. I am not looking at the YouTube chat, and the reason I'm not looking at the YouTube chat is specifically because there are a lot of people who are from actually all over the world, and because this session was originally directed towards Math for America, the chat that I'm paying attention to right now is the Zoom group chat, and anyone who comes in from the rest of the world, you're of course very welcome to be here. But I'm running this session. This was supposed to be a Math for America session for which there are a bunch of onlookers. Okay, great. But linear, we're going to change this word linear. This one is often called affine functions. So usually the distinction between linear and affine is not a big deal, in the sense that when we're doing things in algebra class, both of these look pretty linear. Except that for what I'm going to do with matrices, I want to focus entirely on this kind of function, the most simple kind of linear function, which is exactly a proportion. Because in some sense, these affine functions are not quite proportions, in the sense that if I look at moving across the x-axis by some amount, the y-coordinate that I get in the end, if I look at an x-coordinate and a y-coordinate, they're not exactly proportional because there's this extra b or c. Okay, so linear functions. We're going to do this particular kind of linear function. Now, when we do linear functions, we often apply functions in this way. We often write functions like f of g of x. That's going to give me a certain convention for how I'm going to draw a bunch of diagrams. I will say that this particular way of doing f of g of x, you evaluate from the x first, then you apply the g, then you apply the f. Yes. So, oh no. So I see that there's also a Hangout. Is that right? So I'll say that I don't know about a Google Hangout. I saw a group chat. I don't actually know about a Hangout. I only know of two things right now. I only know of the Zoom and the YouTube Live that we're running at the same time. Great. But so we have this f of g of x right here. And the way that we often think about what happens when you apply functions is when you apply functions, what's happening is that you have an x. Maybe I'll draw it on the right. You have an x, and then a g is applied, and then an f is applied, and then you get f of g of x. Okay, so in some sense it's going backwards. So this is going backwards. And I'm going to use this backwards type of notation as I start talking about some kinds of linear functions. So let's start with the simplest kind. The simplest kind of linear function is one which goes, I'll use capital letters now for my functions, and that's because we're about to do more sophisticated functions. The simplest kind of linear function is from one variable. That looks like an L. Let me just put the one separate. One variable. And it's going to give me one variable. So this is the simplest kind of linear function. So here's a question. If I have this kind of linear function, how many numbers do I need to represent what this linear function does? Feel free to just type into the chat. I think that's probably the most efficient way. Then nobody feels like they have to stop and raise the hand. We would need two numbers if the kind of function I was looking at was the one which is like mx plus b. And I'm talking about from one variable to one variable, the number of linear functions I might have. I'm talking about this kind of linear functions now. Linear functions which are going to be a line which happens to go through the origin. So if I wanted to describe an arbitrary one, yes, I only need one number, right? And you're right, it would be two numbers with the normal way we talk about linear functions. Actually, 1 second. I want to make sure I'm saving my screen capture every so often. So I'm going to sneak past here and move this. I have a keyboard over here that I use. This one makes sure that I don't lose the screen capture. And the reason that's important is because the computer tends to crash every so often. So just a second. Is this actually connected? Oh, interesting. Seems like it is not quite connected. Oh well. Okay, well, in that case, we'll keep going. Sorry about that. With this technology, things sometimes work and sometimes don't. But let's keep going. So we have these linear functions, and we need one number for this. So these are parametrized by one number. When I say the word parametrize, it's just that there's just one number that describes this particular function. And many people were calling that the m, right? Because if there was an m here, if you happen to have a variable, maybe the variable was x, then what would happen after you passed it through this function is you'd have m times x. Oh no. And actually with that, the system actually just crashed. Just a second. So I apologize. With this particular screen capturing thing, sometimes it freezes, but we'll get it back. Okay. Here we go. Okay. So as I was saying, we happen to have we could have a function f, which goes from one variable to one variable. And what you have is if it's parametrized, if that function is called m, then x goes to m times x. Okay. But now that's what you can have with one variable. What if you have multiple variables? How should we try to think of linear functions then? So if we have a linear function with two variables, we could also think of a function, let's call it g, and suppose it goes from two variables and it spits out one variable. Now, if it takes two variables, I guess we would have an x and a y come in. I'll just draw it this way. And somehow this function should spit out some function, it should spit out some combination of x and y. What would be reasonable if we wanted to define what it meant to be a linear function of two variables, where I spit out one thing. So when I say this one var, I guess what I mean is that I put in two numbers and out comes one number. So dot product is an idea, surface is an idea. Actually, surface is often how we might even think of graphing these things. Dot product is something that you might do if you had vectors. But what I'm trying to say is, if a one variable to one variable linear function takes your one variable and scales it by something, it's proportional, then you take one number, m, to describe what it does, and out comes one number. So it's like one number goes in, one number goes out. That's how I'm thinking of my functions. And you need one number to explain how you're scaling it by. And the question is, yes, is it addition or subtraction or multiplication? Indeed, if I'm looking at a general function from two variables, from two numbers that spits out one number, I could do all kinds of things. I could add them, subtract them, multiply them together. However, I'm interested in linear functions. So I want to say that a linear function of these two variables going in is, we're not exactly multiplying, we're not inventing multiplication. We're about to motivate why matrix multiplication has the formula that it does. I'm saying that a linear function of two variables, if an x and y comes in, I saw that somebody had indeed posted, Gary Rubenstein had posted, that this was ax plus by. For some a and some b, maybe let me use specific numbers because that will just let me make it very clear which are the variables and which are the numbers, just for the sake of discussion. And yes, this is in fact what is called this is called a linear combination of x and y. But I just wanted to say, this is a natural thing you might think of. If you started with one number and a linear thing you could do with it is to scale that number, then if two numbers come in, then you scale, then what would be a linear thing to do with both of them would be to do 3x plus 2y, or something with different 3 and different 2. I see that somebody said it's cutting in and out only briefly. Unfortunately, it seems like the internet is more and more saturated these days. So if it turns out that it is cutting in and out too often, then I think what I might end up doing is I might end up just running the whole thing over to the Zoom. But I would actually like to know if it is actually cutting in and out for everyone at the same time, then that means there's a problem on this side. On the other hand, if it's cutting in and out for different people at different times, then usually that's unfortunately the other side. Thank you guys. Thank you guys. Okay. So, right. So I'm saying this is something that you could do to make a linear function. But now what's so special about this? Why is this natural to call it linear? One reason is because it turns out that it also is somewhat proportional. Because if I took this two variables thing, just cut out. So I see it's cutting in and out for a bunch of people, and there's a lot of buffering. Okay. Let me see, what's the best way to solve this? So it's still fine. Okay, so here's what I'll say. Unfortunately, if it seems fine for most people, then again, what is really happening is the internet is just too saturated right now with like different people's connections. The only time I would start to get really, really worried is if somehow it's like coordinated with everybody. Great, thank you guys. And I'm sorry that somehow with the internet teaching, this is what we end up having. Okay, thanks everyone. Unfortunately, when we teach our classes online, we also have this happening with the different people here. Okay, let's keep going. Right. So this is a natural thing to call linear because it's also got a proportional relationship. Because, for example, if I doubled x and y, well, let me give an example. Let's put in an x and y. Let's put in an actual x and y in this particular function. If I put x equals, if I put x equals 1 and y equals minus 1, then what I would get here is I'd get 3 times 1 minus 2 times 1. I'd get 1. But you can, I hope that's right. I often do these wrong. But then after this, what you can do is if you looked at these x and y, and you tried doubling x and y to go with 2 and minus 2, if instead of 1, we used 2, and instead of minus 1, we used minus 2, then the answer is exactly double of the 1. It's 2. So it has the same proportional property that people had said. Okay, great. So this is a natural thing that you'd use for linear. And now the question is, what's a good way well, no, that was a good way. How many numbers do I need to describe a general linear function then? What I mean is if I have two variables going into one variable over here I said I only need one number called m, and it can explain what this entire arrow does. So the point is this function is an arrow, and I can describe the entire thing that the arrow does with just one number. From two variables to one variable, in general, how many numbers do I need to describe what this function does? 2, exactly, you need 2. And for example, up here, the 2 that I used were like 3 and 2. So for some reason, if I just had 3 and 2, the 3 and 2 could describe a function which takes the x and the y, and it spits out 3x plus 2y. So I'm basically explaining that somehow, oh, I see. So maybe that's going to help with the bandwidth. Thanks, everyone. And I can also see the comments, which is great. So I could say that if I have a linear function from two variables going into one variable, then I just need two numbers. Now the question is, how should I write those two numbers? Should I write those two numbers as 3, 2? Or should I write those two numbers as like 3, 2 stacked? Oh, I have an issue when the screen is shared. I can't see the chat, right? So it's like there's a convention choice. What I mean is I could write 3, 2 like this. But there's a question, like what if I chose alternatively to write the 3, 2 in a different way? I have a choice. I could also have chosen to write from the two variables to the one variable. I could have chosen to write like the 3 here and 2. I'm basically saying that I'm looking for some way to write these two numbers down. And indeed, I see the matrix as a linear transformation. That's actually what I'm trying to get to. I'm basically trying to say, rather than first defining here's a matrix and here's how matrix multiplication works, I'm trying to say, let's talk about linear functions. How would I even try to represent them? And in general, a linear function from two variables to one variable, I could write either with the 3 and the 2 this way, or the 3 and 2 this way, but there's basically just two numbers. There was no ambiguity when there's only one number up there, when you multiply by m. So then I want to motivate a bit of why this is a natural way to write down those two coefficients, those two numbers. The reason is because there are also other kinds of linear functions you can make. You can also make linear functions that go from two variables to two variables. To lower the video resolution. Oh, that one might work too. So indeed, it could be that depending on where you are, depending on the internet speed where you are, if you reduce the video quality on the YouTube, it might make it so that the video transmits better. I believe unless we get a situation where everybody simultaneously has video problems, then what that means is on the individual sides, that might be the limiting factor. I will say that from this end, I tried to upload the highest quality video so that people can make that choice after it gets from the cloud. But let's go with an H. An H is from two variables to two variables. So for H, let's go from two variables going into two variables. So now what this is I will have two things being output. And what would it mean for it to be linear if there are two things going out? So two variables going in, I could say that there's an x and a y. Those go into my function. And now I need two things coming out. But I want it to also be linear with respect to both the x and the y. What do you think would be the right thing to do in terms of how many numbers do I need to represent? Or in general, what does it mean to have a linear function that takes two things in and it spits out two things? Feel free to type in the chat, and then I'll start building from that. 4. It does make sense to have 4. It's like a 2 by 2. And the way I want to motivate the 2 by 2 is I want to say, this linear function that spits out a linear, that is a linear function with two outputs, I would expect that to look something like this. 3x minus y and x plus y. This is a fairly boring set of linear functions to come out. Yes, I see, indeed. We need a linear combination for both. Oh, if I look this way, I don't have to have as good vision. So Kevin C says, I just need a linear function for both. Because again, two things go in, two things go out. And the whole point of linear, as far as I was working, the easy part I was using was somehow, if you scale it, if you multiply your x, y thing if you take your two numbers you put in, and you double both, then actually this also doubles. The answer will also double. And that's nice. It turns out there's also some more that happens when you have two variables going in, but I'm not going to necessarily focus on that right now. Instead, I want to say, once you see that you write them this way, it's very natural to say, I can represent any linear function from two variables to two variables as this matrix. And I'm just saying that the matrix itself is just saying, we have a linear function. It takes two things in, it spits out two things, and I will need four numbers to describe what it does. It is most natural to write those four numbers as 3, -1, 1, and 1. And so far, I'm not telling you that there's a certain way to multiply matrices or add matrices. I'm just saying this is my shorthand for writing down a linear function, which is taking in two things and spitting out two things. Now, I actually write my matrices this way. But right now, I'm not really calling it a matrix yet. I'm just drawing the four numbers and putting a box around it. I like this a little bit better because then you can see the shape of it. I learned this from another professor when I was a college student. I saw some professor do this, and I thought it looked better than what I was doing before with some parentheses. Okay, so now we have these linear functions. Now, whenever we have functions, we can think of what happens when you compose them. So now we're going to move towards this definition of matrix multiplication. What do I mean by compose them? Well, I'm going to draw a chain of some things you could do that start with just one variable. If I have one variable, and I apply first a function f, and that function f, what it does is it's going to spit out one variable. And I want a linear function f, so what that function f does is, let's just do multiply by 2. Multiply by 2. And then after that, it goes into a function g, which does something else, maybe multiply by 3. And then it spits out one variable. So this is a very simple chain of one variable functions, two one variable functions chained one after the other. Note, by the way, both of these are linear. Picture is gone. Are you saying that the YouTube picture is gone or the picture on the Zoom is gone? Just lagged. Okay. Again, I apologize for the way that that this quality happens to be. We'll do our best, and what I'll also say is I'm looking forward to always improving how we do this. So after we do this, we'll try to figure it out. Okay. But so here I'm talking about one variable going to one variable going to one variable by two functions one after the other, and these are both linear. Linear means they're scaling proportionally. When you look at this is very obvious how you would chain the two functions together. You see, what I'm saying is that the value of having composition of functions is I don't need to say, if I get 6 in, I absolutely have to do 6 times 2 to get 12, and then absolutely have to do 12 times 3 to get 36. But rather, I could define what's the composition. The composition, which will let me do that all at once, is just what happens when you already know you're going to times 2 and then times 3. So that's times 6. So this is obvious for one variable, one variable, one variable pipelines. But also notice that's multiplication. So the reason it's multiplication is because we're doing linear functions where we're scaling every time. So since we're scaling, we're multiplying by the same factor. If you scale and then you scale again, you're scaling by the product. So it's quite natural that this is multiplication. Actually, why I'm doing this is I wanted to motivate why matrix multiplication is the way that it is. And the word multiplication is used because what we're about to do, the reason multiplication as that word is used is because what we're about to do is we're about to think of what happens if you chain a bunch of these more variables going to more variables going to more variables. So let's go ahead and do the first one. So now let's think of what happens if you start by trying to chain something that's going from one variable, going by some function f, into two variables, and then going by some function g into one variable. I guess here we're going to then briefly remember, what do I need if I go from, let's go from the two variable to the one variable first. This function g is described by how many numbers? How many numbers do I need to describe what happens when two variables come in and then one variable comes out? If I want it to be linear, everything we're doing is linear. 2 numbers, that's right. Because whatever goes into here will have some 2 numbers. Maybe those 2 numbers are a and b. And just to give an example, I'll say if you happen to have x and y, then that particular stage of the function would give you ax plus by. Are we good? I actually heard some audio. So in that case, is there an issue that someone wants to raise? No? Then we're good. I guess we'll keep using the chat thing. Thank you so much for typing in the chat, by the way. This helps me to keep tuned with what's going on. So again, this function g, this linear function g, is just represented by two numbers, and I could call them a and b. And if I got two inputs, then what I would get is I would get one output, which just comes with that combination. I mean, I could even do this with very specific examples of numbers. Well, maybe we don't need that right now. Next, I want to ask the other piece. From the one variable to two variables, if I want a linear function, meaning I only get one input, and I need to put out two numbers, and it's supposed to be linear, what would that look like? What is a linear function that is putting out two different numbers if it only gets one input? What should I do? If the input comes in, I'm going to use another row. The input x comes in. This x is not the same as that x. I'm just over here looking at this part. If this x is coming in, it's supposed to spit out two different things. Yes, ax and bx. Thank you very much, Gary. So what we would need is that this is going to come out with two different numbers. Right, one example of one would have been, for example, if x turns into 4x and 2x. I think that's what I see here from Jeffrey C. Hamilton. If it was that the x spat out 4x and 2x, then that's 1 in, 2 out. And that's very linear. I mean, in some sense, whenever I have multiple outputs, all you have to think about is that just every single one of them needs to be some linear combination of what I put in. And so what would we do to describe this particular one? We would write maybe 4 and 2. And so far, I'm not saying that this is matrix multiplication yet, but I'm just saying that I have some function which is going to turn one variable into two variables. And that function I'm going to represent with this tag, 4, 2 stacked one on top of the other. And then that's going to chain into something else. Actually, since I have some concrete numbers here, I want to write some concrete numbers over there. So I'll replace the a and the b with some other favorite numbers, 3 and 7. That's 3 and 7. Okay? And so now, just like what we did before, I'm just curious if we can save work and try to compose all the way across. When I say compose all the way across, of course, I could take this function that I've written, and I could say, let's throw the number 3 in. If you throw the number 3 in, when you put, let's just do an example. If you put the number 3 into this function, if the 3 sees the 4, 2, so it knows that it should do 4 should multiply by the 3, and the 2 should multiply by the 3, it should spit out 12 and 6. I'm basically saying that right now, this is not a matrix, this is just representing what this linear function is doing. Then we have 12, 6. These are the two variables. These 12, 6 need to go in through this function. And this function says that we should just take 3 times the x. X is the first number. We should take 3 times the 12 plus 7 times the 6. So 3 times the 12. What's going to come out is 3 times the 12 plus 7 times the 6, which is equal to 36 plus 42, which is, this is hard, 78, maybe? 78. So we're saying that 3 goes to 78. Yes, so we're writing, thank you very much for bringing this up, Isabella. Yes, so we have to decide on what convention we want to use. And so you could either have chosen to write the 2 variable to 1 variable as a stack, and then write the 1 variable to 2 variable as a row, or vice versa. But we have to be consistent. And so far, all I'm saying is that these things are just ways of representing what these functions are doing. From 2 variables to 1 variable, from 1 variable to 2 variable, there are a set of instructions, which if I take something in, I can say, follow these instructions, and I'll get something that comes out. By the way, I actually should say, I know that a lot of people, basically everyone in this call is a teacher, so everyone already knows all of these things. So I want to say the reason I'm talking about it this slowly is not because people don't know, it's because I'm trying to simulate what I would do if I wanted to use this to teach high school students who would be asking the question I had when I was in high school of who invented this crazy idea of multiplying matrices. And so the idea was, well, we've got these Thank you, Jeffrey. But by the way, when you say the refresher is nice, I agree. I got my refresher too while I was preparing this course. So I chose to talk about this because I myself did not actually know. I did not really know off the top of my head, why do we do things the way we do things? And so I had to sit down and go and come up with an explanation. This, by the way, is just my explanation. It's not the official one. This is just what worked in my head. And that's just what I'm sharing with you. But so the point is, you're just basically saying we're going from we've defined what linear means from some number of variables to some number of variables. And so it's very natural to try to write these stacks or these rows depending on how many variables in and how many variables out. Okay. But now I want to save work because I don't want to say every time I put in some number, I'm always going to crunch through a lot of this calculation and get something that goes on the other side. I want to do the analogy to what we did with one variable to one variable to one variable, where we just said, oh, it was times 2 and times 3. That's just times 6. So how would we do that? The way to do that here, oh, yes, thank you for all your comments, by the way. So how would we do that? The way we would do that is we might try to say, what happens if you just put in one variable and you generally call it x? And in fact, I'm going to do this again. Well, let's do it with these numbers while we have them. But let's trace what happens if an x comes in. And we sort of started that with the blue. So maybe use the red. So an x comes in. If the x comes in, then what happens? What do you get if the x sees these instructions, 4, 2? What do you get in the second stage? Then I guess quite naturally is that you follow the instructions. Thank you very much. Yes, yes, yes. Thank you, Kim. So it's 4x and 2x. So everything I write in this central zone is just saying that's what I got after stage 1. Now 4x and 2x come in. So what do I get when I do one more stage? Well, the one more stage says 3 times whatever is the thing on top plus 7 times whatever is the thing on the bottom. Right? So because that's just what the instructions said. The instructions said I should take 3 times the thing on top plus 7 times the thing on the bottom. But that's just 3. Oh, I ran out of space. Sorry. So that would be 3 times 4x plus 7 times 2x, which is 12 plus 14. Well, let me do this. You know what? The actual answer is less important than what I'm doing. This is really interesting. What did I just do? 3 times 4 plus 7 times 2. So what we just got, yes, and indeed we can simplify this. We can say it's 12 plus 14, which is something, 26 maybe. So we could get 26. But what I really wanted to get at is this. So this 3 times 4 plus 7 times 2, we have just gotten one of the key parts of matrix multiplication. In fact, when you do matrix multiplication, a lot of times, actually, the way I learned it at the beginning, I didn't know why, but I just learned that whenever I see 3, 7, I'm going to draw them this way because I got used to this after watching a professor when I was in college, times 4, 2, I just learned to memorize that you take this is 3 times 4 plus 7 times 2. So that was how I learned matrix multiplication. But look, this is exactly what you get if you just are chaining together 2 linear transformations, right? So what we said is, this is one reason why I want linear transformations, which aren't like ax plus b. This is not criticizing anyone who gave that answer. That is what I call a linear function too. It's just that for the purpose of explaining to a high school student, let's drop the plus b. And so this, yes, this is how I'll learn the matrix multiplication, right? So it's just somehow, it's just chaining. You just chain it. But now let's do it with, we could do it with more dimensions, more variables to more variables to more variables. And we can do it with letters too. But let's just go ahead. Let's just see what happens. So that was 1 variable to 2 variables to 1 variable. The next example I wanted to go was what happens if you chain from 2 variables going to 3 variables going to 1 variable. So how would this work? So now I need to describe all of these. Yeah. So by the way, I also thought this was cool when I finally realized this, because again, otherwise it's just like, who invented that stuff? So okay. So what happens? 2 variables to 3 variables to 1 variable. Let's do it with numbers first. And to be perfectly honest, if you do it with numbers, it's the same with letters. And I just prefer numbers, so it's clear what are the variables which are passing through and which are the actual function itself. So from 2 variables to 3 variables, let's do that first. If I have an x and a y, which are going to go into this, which are going to feed into this, what do I need to describe a 3-variable output? What would that look like? Like, maybe just give me an exact example with some numbers. You don't need to say how many numbers. I don't want to know how many numbers do I need. I'm basically saying, can you give me what would be a 3-variable linear function of 2 inputs? And indeed, it will have things like ax plus by, but I need 3 variables. Yes, thank you. So I'll just use exactly what Jeffrey Hamilton wrote. He said 2x plus 3y, x minus y, and 6x plus 8y. Okay, so we put those things through. Now the question is, what tag, like what sign do I use to describe this 2-variable to 3-variable? I should just be consistent. The way that we were making our signs is we always drew some rectangle, and we would go across each row based on what we call the coefficients, how much we multiply the x and the y by. So as I try to write down this sign would just say 2, 3, 1, -1, 6, and 8. Okay, so that's one such function. I also want to describe a 3-variable to 1-variable function. For that, I guess I'll use a different color. Let's just say 3 variables, by the way, are x, y, and z. Could somebody please just give me some linear function of 3 variables which spits out only one number? I guess I shouldn't have called them one var. In some sense, it's just like one output. So it's 2x, thank you, Isabella, 2x minus y plus 3z. Okay, and indeed, I shouldn't have called them var, but the reason I'm calling them var is because I will say, actually, the way that I learned functions of many variables was because when I was in early high school, I was getting into computer programming. Oh, did I make a mistake? 3. Oh, I see. Maybe somebody is combining them already. You guys are faster than me. I was just trying to get some numbers, some example here. Okay, great. But I just wanted to say why I call them var is because I first got comfortable with functions when I was writing functions as a computer, like for computer programs. Because when you write a computer program, you have these functions and they have some number of variables coming in. Int foo, int bar. Thank you, Seth. It's like somehow when you have these number of inputs going in and you have something going out. And that's how I always thought of it. Okay. So now, and it's not true that there's only one variable in the sense that somehow this still involves all 3 of the variables, but I'm just saying there's like one number which has come out of it. And so that's why in this machine, I'm just seeing how many numbers am I tracking. Well, over here, I need to write the tag for this, and the tag is going to be just reading the x, y, z in order. The only thing special about x, y, z in order is that's the order from top to bottom, as I've been calling them the first variable, or the first input, the second input, the third input, and so on. So let's write the tag. The tag is 2, I'll write it over here, 2, -1, and 3. So I have these 2 different tags. And now the question is, what happens if I try to compose these? If I want to compose these, I guess I just have to go and trace what happens. If I take the xy, I get this thing. And now what happens when I take this thing and I try to do that? Here's where it starts to become a little bit more algebraically complicated. However, it's worth doing with just some numbers, because once you see it, then the whole thing falls out. So here's what I'm going to do. I need some space. So I want, oh yes, thank you. So what's going to come out, by the way, is if I wanted to write a tag for it, that tag would have 2 numbers horizontally, because it's like x and y came in and only one thing came out. But I want to actually work out that what the tag looks like. I'll need some space, so I'm going to wipe out the yellow stuff. But I want to say that this green thing here already represents the particular function we chose from 3 variables to 1 variable. So let's clear this part out. I don't need it because the tag here has all the information. Instead, all I have to do is the hard part, which is to do some kind of calculation of what happens if you apply 2, -1, 3, where 2, -1, 3 means we're only going to get one number out. This thing here this is a very long equal sign. Okay, so this one number which is coming out is one equal sign. It's just, I'm going to write it down here. Some number comes out, and the number that comes out is the 2 multiplied by the first of the 3 inputs to that function, 2x plus 3y. Okay, So that's saying that there's this 2 here, and that 2 is going to be multiplied by the first input, plus -1 times the second input, plus 3 times the third input, because that's what this 3 variable to 1 variable was doing. 2 times the top, -1 times the second, 3 times the third, add them all together. And so here maybe I can even try something with color. -1, so it would be -1 times x minus y, and then there's the 3, plus 3 times 6x plus 8y. Okay? Now, if I have all of this, exactly, somebody had pointed out that it's actually going to have to be, we have to express the composition as 2 numbers. But what were those 2 numbers? Those 2 numbers were the coefficients of x and y in this complete thing that we put together. So that means we need to rewrite this thing as something times x plus something times y. And these 2 somethings will be the 2 numbers that we use as the tag that describes what happens when you go from 2 variables to 1 variable. But this is very, very convenient, because there's a reason why I chose these colors, just so that you can see, this is the 2, this is the -1, this is the 3. But actually, I care less about the yellow staying together. I care more now about separating apart what's happening with how many x's and how many y's. So if I start to collect all the x's, what I get is I get 2 times 2 from the first one. That's a times sign. I get -1 times 1. I'll write it this way. Plus -1 times 1 from the x part. And then here's the coefficient on the x with the 3 times 6. Plus 3 times 6. Okay? So that's how much multiplies by the x. And yes, exactly. Matthew, thank you very much. You're saying now you can actually see the row being multiplied by the column. So as we put this thing, and actually that's a nice way you're putting it. You're basically saying this 2, -1, and 3. Thank you for saying that. The 2, -1, and 3, if you're going to look at how you got this 2, -1, and 3, those were the coefficients of the x. So in fact, what you actually did is you were going to take the things that had the x's anyway. The things that had the x's, those were the coefficients of the first column. That was this column. So the whole point is that when you go and do this with numbers, I'll be honest, whenever I do this with students, I find that if I write lots and lots of letters like X, Y, Z, and then A, B, C, D, E, F, G, unfortunately, a lot of first-time learners, it's just too many letters, because maybe they don't immediately know, they don't have the intuition for which are the numbers that are they're just the variables coming in, and which are the numbers that are describing the entries of the matrix. They have different roles. And so that's why I actually generally like to just go and ask students or anyone, just give me some numbers. Because at that point it's clear there was nothing special about these numbers, because they came from someone else. And these x and y's, those are tracking the inputs. Okay, but so what we have here is in this pattern, we exactly got this 2, 1, 3 multiplying against this 2, 1, 6, because we wanted to pick out all the things that were in front of the x's, since that was our whole goal, to get the things in front of the x's. For the things in front of the y's, then I need to pick out the 3, the -1, and the 8, which are exactly this 3, -1, and 8, which are exactly that 3, -1, and 8. So if I do that, then I would get 2 times 3, and then plus -1 times -1, and plus 3 times 8. And when I put everything together, now I can say what is the tag that represents the entire composition. The tag that represents the whole composition from 2 variables to 1 variable is supposed to have 2 numbers. And actually, I don't know if I really want to write those 2 numbers, but I'll say it's going to be this and this. I'll use stars. There's 1 star, which is all of this stuff. And there's something else. I don't know what to call it. I'll draw a different kind of star. A star with 5 points, which is that one. And so I've just gotten that if I want to compose this all the way through, then what I should do is I should take this row and strike it against the first column, and that will give me the first entry. And then take this row and strike it against the second column, and get the second entry. Oh, it looks like our Zoom call has stopped. Now I'm a little bit curious what happened, because if the Zoom call stopped, I might have lost you guys. So I'm going to attempt to reconnect into the Zoom. Just a second. So I apologize for people who are watching on the internet. I want to make sure that I have a connection, and I see the reason why that the connection dropped on my Zoom has something to do with my internet. Just a second. And the Zoom is very important for me because that will let me be able to see what people are saying. So I have a suggestion. The suggestion is, anyway, we usually put a 10-minute break in. This seems like a pretty good time for a 10-minute break because we have just figured out the two variables to one variable. We've just gotten matrix multiplication. And so what I'll do is, while I attempt to get my Zoom back on, let's take a 10-minute break and let's restart at 6:30, okay? And I'm going to try to reconnect my internet to get my Zoom back in. Great. Okay, good. So we do have some contact here. Just letting you know, we're still going to take the 10-minute break anyway because that was a natural place to stop. And I also saw some people asking about the setup. I'm of course happy to talk about the setup that I'm using. As you already saw, the setup is not perfect in the sense that it sometimes crashes. So maybe towards the end, if people are curious, I can have some of the interaction about that piece. But for now, yeah. We can take, well, you know what? Since we're taking a break anyway, I'm happy to just talk about that now. So people are wondering, what exactly am I using for this? In my opinion, actually, all that's really going on here is that I happen to have a screen behind me, which is green. If you want to have a very, very clear background, the secret is just that the screen in the back needs to be green enough. And then you can use a program to remove the greenness. I believe that Zoom even does that for you. And so, actually, here I'm going to reveal some of what's actually going on by turning off one of the filters. Where are we here? How do I actually do this? So this is the blackboard, video camera. That's the one. No, this is the one. That's right. So I'm about to go and remove my greenness in the back, and then remove this thing which is superimposing the two parts. If I could read, here we go. There we go. Take that off. The problem is that my vision is not good enough to go and see. Just a second. Cancel. What were you doing here? Filters. There we go. So now you can see what's actually going on behind me. That's all there is. This is just a green screen. So what's going on is there's just a green screen in the back, and you guys can see that now, right? You can see that there's just this pure green in the back. I think I turned the filter off, so you should be able to see there's green. The idea is to make the green screen as evenly lit as possible. If it's as evenly lit as possible, that uses some of the lights. I have a bunch of lights which are around the room, and the hard part was to make it really evenly green. Then the next thing is, let me put that back on. So once it's evenly lit, it makes it so that somehow you can put anything else that you want on the back. So now what I exactly use is I just happen to have a program. I like to use an operating system called Linux. And so on Linux, I was able to go and get the source code, the computer code for a program that lets you draw. And I just adjusted the colors on that to make it do what I wanted. But if you happen to have a license to use various Microsoft products or Apple products, effectively all you need to do is you just need to merge together. You need to have something that you can draw on. And the thing that I draw on, actually, I'll lift it up. So the thing that I'm drawing on is a tablet. It's just anything you can draw on. But the key is there's this wire coming out on the top. So this wire on top is an HDMI output. So anything that has an HDMI output, you can potentially move it, take that input and put it into anything else that you want. It is not absolutely necessary to do it this way, but I guess I don't know that easy of another way to do it where another computer is putting everything together. So effectively what's going on is I have this thing I'm drawing on, and I have another computer which only does one job, which is to merge everything together. And that other computer takes an input from this HDMI of what I'm drawing on. So in a schematic, what's really going on is that there's a camera which is taking the green, and then there's also the output of the tablet I'm using, which is going into a computer, and then that computer uses a free program. The program is called OBS Studio, and that free program takes these two signals and it merges them in this way. And that same program, OBS Studio, has a button you can use to do a YouTube live broadcast. It's actually less, I guess if you use Windows, you might be able to even make that program send the output to a Zoom call. I think this is possible. I just don't happen to have a Windows computer to test that on. But effectively what happens is that there's another computer out there which is doing this merging and then the broadcasting. And the cleanness of the background is basically a function of the fact that there is a very green piece of cloth, like I think it was like maybe $30 or something on Amazon, which got hung on the wall, together with enough lights to illuminate that background, so that the free program OBS Studio was able to figure out what is me and what is not me. And then I just happen to be using this tablet to draw on, but if you have anything else which can output an HDMI, then somehow that can be sucked in by the computer. It does use a hardware item, which is it's an HDMI capture. It's like an HDMI. It's like we're doing functions, right? It's basically, it has to take an HDMI, which is coming from my drawing, and it has to convert that into a USB. So there's like this device which takes in an HDMI and it spits out a USB signal, which and then you can plug it into your computer, and then the OBS Studio works. It's a capture card, right? And I'll say, another thing I'm doing with this at the same time, I'm actually also recording this because YouTube, this is recorded on a couple of different ways. One is everything you put on YouTube Live is automatically recorded by YouTube, and it becomes immediately available as soon as you stop to anyone in the public. My students at Carnegie Mellon, I think it's helpful for them because sometimes right after the class, they're able to just go right back into it and go and see, what exactly happened. So yes, so that's what I'm using. I decided not to use Zoom for my teaching at Carnegie Mellon only because my understanding of Zoom is that it's optimized for like a teleconference where everyone is equal and everyone's supposed to be participating roughly equally. But I mean, we're all teachers. Of course, we do want all of the students to participate also. But I think from the student's perspective, it's more important for them to have as clear a picture of the instructor as possible. And if they have a less clear interaction with the rest of their friends, that's okay. And so the way that we're doing it in our class at Carnegie Mellon is exactly this. We actually have exactly what we're doing here, where there's this thing pushing the live stream on YouTube, and then in the background, there's also this Zoom chat. And with my students, because the class is not, I don't know how many people are here, it looked like there were 7 screens. My class is not as big, so we sort of can all fit on the same screen. Or maybe at most 2 screens. And then I can actually see the students as they wave their hands. Because what happens on the Zoom is they have some question, and they just go and raise their hand, and I can see right in front of me, oh, that's that person raising the hand. It doesn't work as well here just because we have too many people. So that's why at the beginning I said I can't seem to get any feedback. Yeah, so that's what I'm using. I actually gave that same advice to my university to say, if people wanted to do things this way, I'm happy to suggest what equipment to get. In some sense, I'll say, as all of us are trying to teach remotely, I did this because I happen to already know how, because as some of you may know, I already run these daily live streams on YouTube. I also happen to, I was filming an online math class for a long time for middle school students. So I already figured this part out. But it's not a secret. And what I advised to the administration was, if you're going to teach remotely, this sort of equipment investment would actually make it possible for each teacher to deliver, this type of experience. My biggest downside with this is that the YouTube does lag, and unfortunately, that seems to be because the whole world is moving into streaming video all day, because all of the teachers, all of the professors, everyone is teaching online right now, and I think that's putting a clog on the internet. Yeah, great. I mean, sure. Yes, the good internet connections, that's tough. Yes, I will say that if the internet connection is not strong enough, then it can actually be quite hard. I'll also say, what platform of software did you say? Here's what I'll say. The basic ingredients, maybe I can share afterwards, because I was just talking through them now. I'm happy to share afterwards. I can communicate with Math for America, and I can share with what we're using. And I would not be surprised if you can do a better job. Yes, it's a longish answer. But I wouldn't be surprised if you can do a better job, because for example, I didn't have certain of those tablet type writing devices that maybe you could use. I just used what I had in front of me. Great. So I guess that finishes the break. And so what we had here is we have now actually derived why the way that you multiply those two matrices is, and again, this is how I always thought of it in my head before looking at this way of thinking. The way I always thought of multiplying two matrices is if I have three numbers like this multiplied by something like this, which has, three numbers in each column. Somehow the way I always thought of it was you take the first column and then you multiply it across by everything there. And then what you get is, and you'll get one number. So you'll get one number, that's the yellow one. Oops, I want to switch this to yellow. You get the yellow one. And then you go and take the other column and multiply it by the same row, and you get the other number. So that's what we usually memorize. And somehow, yes, forward to the state. That would be great. Actually, it's not rocket science. So yes, so somehow you take these two things, and this exact thing is exactly what we did. So by the way, this also shows why matrix multiplication is associative. So yeah, dot products of rows and columns. Thank you. Yes, Matthew, that's exactly right. It's dot products of rows and columns. And here's what I'll say. Instead of me doing another version, the other version would be 2 vars to 3 vars to 4 vars. Maybe you can already see by now what kind of thing you would do. And so if you do this, if you just work it out on your own, you'll be able to see if I just had this one being 4 vars, I would just have 4 rows of stuff here. It would be a 4 by 3 if I change the last one into a 4. And you could see the pattern. And that would be the important part. I see there was already a question. Eddie says, is there anything specific that's taught in elementary school that directly leads to this in high school? Examples that elementary teachers can tell their students about. So I'll say, to me, the best example I used, the one that made sense to me was just this idea that you're combining 2 steps of a machine. So it's like this I was going to times 2 and then I'm going to times 3. And the idea that you don't need to always take whatever number, times it by 2 and then times it by 3. You can just do the 2 times 3 once and you save work. You just times 6. So maybe that would be the best analogy I would give. You do that kind of it's this way of saying, I want to save a step. For example, if I was, here's something I would use. When I'm working with elementary school students, I'll often talk about these kinds of number games where I say, give me any number you want. Multiply it by 3, and then subtract 9, and then divide it by 3, and then add 3, and you're back to yourself, right? It's basically just composing functions, right? It's like these magical things that you tell elementary school or middle school students, just do this sequence of steps, and your answer is always the number you started with, or maybe your answer is always 9 or something. And so the idea is, if I've gotten this whole chain of commands that I have to do, you don't have to every single time do the command, then do the command, then do the command, then do the command. You can once and for all do the whole thing, and then just go, boom, you're there. Okay. this will take a bit for kids to do. Yes, we often say to show every step. The input-output boxes. Yeah, perhaps. I mean, basically, I'm just thinking of these function machines. I actually grew up learning about functions as function machines, both in my textbooks, also from my teachers, and also when I programmed computers. And that's to this day still how I think about functions. They are function machines, and there are some labels that say, tags that say, what is this function doing? So that's actually how I think of it. But because I've just done matrix multiplication this way, this has now answered a question that I was curious about. I was curious about this. I'll be honest. I hadn't thought about this deeply even before I prepared this class for everyone. I was just curious. Why is matrix multiplication associative? I mean, that's actually a very, very fundamental question. Why is it true that if I go and take two matrices and I multiply them together, or to make my life, something like this. Let's put a third matrix. Actually, whenever you multiply matrices, the dimensions have to match in some way. So I guess I'll put them like this. Okay. When you multiply these matrices together, somehow you're allowed to do it in two different ways. You could either multiply those two first, and then you'll get some answer. And whatever that answer is, you then take this times that answer. But that happens to be always the same as what happens with those exact same three matrices. I see that there were other people who also used function machines. So, yes. And exactly, it doesn't matter which machine it goes into first. Well, the best way that I came up with explaining this was that I actually just told you the matrix multiplication was a way of consolidating any two functions. I guess that's what you just said, right? So the thing is that I've got these function machines. When I drew this thing, like the idea of this matrix multiplication being associative, at first, if you tell someone, my definition of multiplying matrices is put some numbers here, put some numbers there, put some numbers there, then like somehow if I put all these numbers in, and this is the funny rule for multiplying, if you make that definition, then to prove that this is associative, meaning it won't matter whether I do that mysterious operation here first or whether I do the mysterious operation here first, that could be harder to prove because you have no intuition for why you define the function that way. For why you define the multiplication that way, right? Because if somebody just told you, here's a rule for multiplying, well, why in the world should it work that you just do this first and then do that? It should be the same. But on the other hand, it is true that somehow the functions I'm using here are all linear. But it is also true, in fact, even if I have non-linear functions, meaning if I have just like any old functions, I think I know what you mean. It's like if I use linear functions to think about matrices, so that every matrix actually is what we call one-to-one correspondence, in the sense that for every matrix, there is a linear function that's doing what it represents. And by the way, for every linear function, there's a matrix which represents what it does. It's like back and forth. Then I can think of this composition. This is a composition where effectively what's going on is that the first one this is representing an F, and then it does a G, and then it does an H. And this is where it's doing an F, but first we figured out what happened if you did G and then H. What I'm saying is, when you take functions, if you first shortcut the F and G, you first go and, not commutative. Thank you very much. That's very important. I'm not allowed to say apply F and then apply G is the same as apply G and then apply F. Actually, it's not true in general with functions. If one of my functions, right, let me just do some quick examples. If I have a function where f of x equals 2x and another function where g of x equals x plus 1, in general, functions are not commutative. If you do f of g of x, let's just put actual numbers. That saves me time. If you do f of g of 0, my favorite number, then this is equal to f of 1, I think. Yes, which is 2. But if you do g of f of 0, then this is g of 0, which is 1. So unfortunately, functions are not going to be, like when you compose functions, it's not commutative. You cannot change the order that you do them. However, functions are associative in the sense that this is just saying I have stuff that goes to stuff, which goes to other stuff. And if I just found a way to summarize what happens when you do f and then g, well, then I just have to write that down, whatever that is, and then I can use that with h together. 0 is my hero. Yes, whenever I'm doing any example, if I can put 0 in to help me quickly solve it, that's what I like to do too. But so what I'm saying here is that somehow, because what we did is we just said it's the same as functions. 3 functions in a row, you can do these 2 first, or those 2 first. It's the same. Okay, just a second. It says my battery is running low. So what I'm going to do is I'm going to attempt to run this charger to this computer. Please bear with me a moment because my charger is far away. Okay, I'm going to step off camera for about 30 seconds as I plug something into a different spot. Zoom apparently uses more battery than I expected. Let's do this. Great. Okay, so we have that. Okay. Don't unplug the wrong cord. Thank you. Yeah, basically what I just did is I was originally charging this tablet I'm drawing on, and I thought that the Zoom call would last, but apparently the Zoom call doesn't last all the way through. Okay, let's continue. Right. So, but by the way, this thing gets for free now. It got us that matrix multiplication is associative. For free meaning I didn't have to do any complicated stuff where I go and actually put A's, B's, C's and attempt to deal with 3 matrices. Actually, this would be a nightmare. If I filled these with different letters and I put all of this together, then I would have a trouble. How you learned about functions has a strong effect on on this associative property. I agree completely, Matthew. You're right. And that's where, when I think about the functions as machines, that makes my life a lot easier. Sorry, again, back to those function machines. It's like putting clothing on. Exactly. That's also another way of putting it. It's like and actually I do that sometimes. Sometimes I have a shirt, a thick shirt, and a jacket that's kind of tight over it, and a t-shirt underneath. And in fact, what I will sometimes do when I'm lazy is I will just take off the thick, it's a button-down shirt. I'll take off the thick button-down shirt and the jacket together, and I'll call that my extra thick jacket. And this is in fact what I did quite regularly for some time because I was just lazy. Another example, I guess that's not a good example, but that one's the best example that I can think of right now. But indeed, if you just think of these functions as, putting them in, putting a shortcut for the later stage, and then earlier stage goes into the later stage, it's the same as put a shortcut on the earlier stage and then feed it into the later stage. So in fact, the entire piece of associativity for matrix multiplication all just boiled down to trying to explain why, if I have these 2 matrices, this notion of multiplying them lets you write down what is the composition of applying those 2 functions one after the other. Okay. So this gives us matrix multiplication, and this satisfies the curiosity for why in the world would anyone invent something like that anyway. But now, I will say we're still not quite done, because what effort does that save you? Suppose you now know that you have this way of multiplying matrices. The next question that students will ask is, but who cares? Is this just to get more homework problems? Is there an actual application that makes life more efficient if you know how to multiply matrices? One answer is, of course, if you can multiply by the inverse of the matrix, you can solve these equations. And that's something that I think is often taught in all of these books and in these classrooms. I want to show you a different one just because of the fact that, again, I don't feel right explaining to teachers something that teachers explain more times than I do. I want to show something that might be different. So the example I want to show might not necessarily work so well in a classroom unless you have students who are maybe looking for the next challenge. Well, maybe it would. Depends. It depends on the classroom you have. But I wanted to share this because also whenever I do these professional development sessions with teachers, it's fun to geek out about math. And I want to geek out about Fibonacci numbers. So Fibonacci numbers at first seem like they should have nothing to do with what I was just talking about. Fibonacci numbers are this sequence, and the sequence goes like this. It goes 1, 1. And then you always add the two previous numbers you had. 1 plus 1 is 2. You add the two numbers you had before. 1 plus 2 is 3. You then add the two numbers there were before. 2 plus 3 is 5, and so on. 3 plus 5 is 8. 5 plus 8 is 13. 13 is 21. We get this nice sequence. We often will label the Fibonacci sequence with some F's. I think I'll call it. I'll name it this way. I often like to call F1 to be the 1, F2 to be the 1, F3 to be the 2, F4 to be the 3, and so on. It's just going in this way. I'll explain why I like this way of naming them. There's not really a right or wrong way. Some people might call the first one F0 instead. The reason I like this is because I often like to say F0 is 0. And that's because if I were to put a 0 on top, it would still satisfy the condition that the sum of the two numbers is always the next number. So 0 plus 1 is 1. And I could actually say that's F0, and something about me likes to say that F0 is 0. This is just a convention. But I'm just writing all these F's because I now want to talk about how you can find the 1024th Fibonacci number. If I want to know or some number around 1,000, if I want to know a huge Fibonacci number, how much work is it going to take? For example, what if I wanted to know the 1 billionth Fibonacci number? At first, that seems like it could be an enormous amount of work because you have to do a lot of steps. As some people who maybe have learned about this before know, there is, by the way, a formula that will give you the nth Fibonacci number. Yes, there is an explicit formula for it. You could write down something that has some square root of 5s in it. It's related to the golden ratio. And I'll say the first time I ever saw this formula when I was a student, I just didn't quite know where this came from. Binet's formula. And yeah, there's a nice formula for these. But how to get it? Or rather, suppose you don't want to go through a certain proof to get it. There's another way to get a fairly efficient way to calculate a huge Fibonacci number. And that uses matrices. In fact, you can even use the matrix thing to prove Binet's formula. Matrices. I'll give a hint. The hint is that it turns out that we can write an interesting function which will take two variables and it will spit out two variables. But this function, it will be the same function I'm going to use over and over and over again. Maybe I need more space. So I'll put another two variables here and another two variables here. And this function is going to be the same function I'm going to apply a whole bunch of times. But it will have the nice property where if I feed in, let's feed in some very specific numbers. If I feed in 1 and 0, after one stage of this function, I'm going to get 1 and 1. After the next stage of this function, I'm going to get 2 and 1. And the next stage of this function, I'm going to get 3 and 2. Something about me wishes that I could do this one more time. Oops. I should actually have left more space, but let's say two variables. The next one is going to spit out 5 and 3. So do you see the pattern, what I'm trying to do here? Well, no, sorry, what the pattern is, I'm trying to say, what's the pattern of these two numbers, those two numbers? How am I getting the next two numbers? What numbers am I writing down? Well, I'm trying to do something with Fibonacci's. So what I'm always trying to write down is I'm always trying to write down sort of the next two Fibonacci numbers, but not really the next two. It's almost like it's sliding in the sense that if I had 1 below and 2 above, that turns into 2 below and 3 above. If I had 3 above, that becomes 3 below and the next Fibonacci number 5 above. And I claim that there's a nice two variable to two variable linear function that turns this one into that one into the next one, and just keeps going. Yes, thank you. X plus y, x. That's a powerful function. Because look, if I have x, y, and that's spitting out x plus y and x, this has the property that whatever the two numbers are that come in, it's going to make the first output. Remember, this function is outputting two variables. So the first output of the first of the two outputs is just the sum of those two things. That's, by the way, why 0 plus 1 is replaced by the 1. The second output we're making is copying the first input that came in. So that has the property of like sort of saving. It's almost like a save function if I think about it that way. right? I'm saying I've got 1 and 0. Save the 1, but call that my second output. Call that my second number. And for my first output, add together the two inputs that came in. If you add together the two inputs that came in, then you get that. Okay. But by the way, that's exactly what's going on every single one of these. Yes, so Paul is right. We just need to raise the matrix to that power and then multiply by 1, 0. And that's an emoji that I don't know how to type. But you guys, I'm afraid I just don't know how to type those things. But yes, I get it. So somehow, all you have to do is the same thing over and over again. This, I claim, this is going to explain why matrix multiplication saves you a ton of time, and also why the associative property is so important. You see, because this linear function is the same one. We're going to do it a whole bunch of times. And in fact, what's my tag, the way I'm writing down this linear function, it is just 1x plus 1y, and then 1x plus 0y. It's this. That's my tag. But it's the same one every single time. So, and now here's where I'm going to have a bit of trouble with the plus minus ones. I'm always off by 1 whenever I do this sort of stuff. So now let me actually label the f1, f0, and so on. This very first thing I have with the 1, 0, this is f1, f0. Okay? And I'm putting that down so that I can start noticing some patterns. I mean, I see that, Paul, you already see it, but I'm going to write it down a little bit more slowly. You see, these two numbers, this thing is I'll write an equal sign so it's clear that those are the same. This is f2, f1. So in fact, what I just wrote here is a certain matrix multiplication. This is the sentence that f2, f1 is equal to 1, 1, 1, 0 times f1, f0. But that's powerful, because now we're going to start chaining and chaining and chaining and chaining. Because the next one, this one here, is f3, f2. So in that case, if I wanted to go all the way from the f1, f0 to the f3, f2, I would get the following sentence. I'll just write it here. f3, f2 is equal to, there's going to be a 1, 1, 1, 0 times a 1, 1, 1, 0 times f1, f0. And here's the comment I made about associativity. Strictly speaking, all we had shown, yes, and for a longer time, right, oh, wait, okay, great, great, great. Let's see, stopping more often. Let's walk through the 3 white boxes, okay. So in that case, thank you very much for bringing this up. Let's go back through the 3 white boxes and talk about why all of these things are true, also because the video had done some jumping. So let's look at these 3 white boxes. So here I have the f2, f1. That's just these right here, okay? And the f1, f0, that was just this 1, 0. And we saw that when I want to go from one of these pairs of numbers to the next pair of numbers, all I do is I have to multiply by this 1, 1, 1, 0 as a matrix. I actually should say, when I say multiply as a matrix, is there a reason why I put f1 above f0? Could it be switched? Yes, the answer is yes. If I switch it, everything would be the same, except that I would have to do some switching of the 1, 1, 1, 0. It wouldn't exactly be 1, 1, 1, 0. It would still have 3 1s inside it, but they would be in different places. But I'll say this particular piece, like what I just did here, this matrix multiplication. Oh yeah, thank you very much for asking me why this thing happened. Yes, the 1, 1, 1, 0, thank you. The 1, 1, 1, 0 is not taking that 1, 1 and taking the 1, 0. No, the 1, 1, 1, 0 is the tag saying the function which takes the x and the y. It spits out the sum of x plus y, which is 1x plus 1y. That's why it's got 1s there. And the second output is just 1x plus 0y's, which is there. Thank you so much for asking. Please do ask whenever there's something like this, because it's my fault. I didn't explain it carefully enough. Okay, good. So, and then over here, what's going on is that this application of this one function, by the way, these 3 boxes are just saying if I were to actually multiply these two matrices, the way we multiply matrices, that's actually going to give me those two numbers. And indeed, if you can see, take this, put it up there, and you have it. Another way to think of it is, well, we already just know we can do something with this matrix. I was basically trying to motivate that it's the same transformation, xy goes to x plus yx, that I do a second time. And so if you do it a second time, then you get this yellow statement, which is whatever is at this stage, that's what you get if you start with something which was the f1, f0, and then do two of these. But if I wanted to simplify that, I could actually first say, let's just multiply them by each other. This is actually how we often write the power of a matrix. So oftentimes, the way we write this is we write f3, f2 is equal to, we write 1, 1, 1, 0 squared times f1, f0. So the goal of this is just to write down, this is just shorthand, saying I would have to multiply two of them together, but because matrix multiplication is associative, I can first multiply these, find out what it is. It's sort of like that times 2 and then times 3 is always times 6. I could just figure out what this is, and then I could do a forward shift by 2 of these steps by just doing that. But now we can see what happens. If I actually wanted to do more of these, if I don't want f3, f2, but if I want like f1025, f1024, I could also do that by putting the appropriate power. So if I look at the power, actually the way I always do these things is I look for a pattern, because you could always prove that carefully if you wanted to, but the pattern is already good enough. This 2 is telling you how much you increase each of these indices by. This was a 1 and a 0. They become 1 plus 2 is 3, 0 plus 2 is 2. And it makes sense because every time I move one step forward, I will increase the indices. Yes, exactly. I see n minus 1. So for example, if I wanted to know what is, I'm going to go to the next screen. Well, no, I'll write it here first just because it's the same. It's right next to it. I'll use a different color to emphasize that this is not the same equation. Oh no, it's not big enough. Let's try this. If I wanted fn minus 1, if I wanted to know what that is, then this is equal to, this is the 1, 1, 1, 0 to some power, I think you said it's n minus 1 power, times f1, f0. So this would be a way of finding a very big Fibonacci number. Aha! Yes! So now people are asking, why do I care about f1025? That is a very carefully chosen number. It's because if I have f1025, I want to go and take, so when I'm finding the 30-second term, yes, there's the two ways to do it. Right. Yes, thank you for saying that. If I want to have the 30-second term, I could either have f32 up here, being f32 and f31, or I could put the f32 down here and have f33, f32. And I wanted the f1025th term just to go and prove a point. But if I want the f1025th term, then my power is 1024. Sorry, if I want f1025, f1024, I'll put 1024 there. Watch what happens. So if I care about f1025, f1024, this is a matrix. It has two entries, one above the other. Power of 2 is significant. Yes, that was on purpose. Well, significant in the following sense. It will let me make my first explanation, and then I'll show you another way to do it, even if you don't have power of 2. But the first one is the clearest one to explain. Power of 2 means 1, 1, 1, 0 to the power of 1024 times, we can now remember what is f1, f0. It was supposed to be f1, f0. f1, f0 is 1 and 0. That was f1. This was f0. Okay, so we have all of these. Then I just need to know power 1024. At the beginning, this does not look like it saves us any time at all, because I still have to go and multiply. Now it's a matrix, 1024 of them. The reason power of 2 is significant, I learned this the first time. The reason power of 2 is significant is something I learned the first time when I was doing computer stuff. It turns out that it only takes about 10 operations to get a matrix to the power of 1024. It's like this. And I'll not do it with a matrix first. Well, why not? I'll do it with a matrix. Let's do it with a matrix. I would start by squaring it. 1, 1, 1, 0. When you square it, that's just multiplying it by itself. I guess I could do that, but that's not the point of this particular part of the lesson, of this particular lesson for students anymore. I'll say you could do that if you wanted to. That's one operation, one multiplication. So this is 1, 1, 1, 0, 1, 1, 1, 0. I'll call this one operation. But now, what I'll do is I will not multiply that by another 1, 1, 1, 0. Multiply that by itself and get 1, 1, 1, 0 to the fourth power. That's equal to 1, 1, 1, 0 squared. So I guess I'd write it again. 1, 1, 1, 0 squared. But I already know what those are. Yes, squared. I already know what each of those are. Assuming I did that operation, I'd get some 4 numbers. Multiply that matrix by itself. What I'm emphasizing is the costly thing for me to do is to multiply 2 matrices. So I start by multiplying 2 matrices, I get an answer. Then I take that answer and I multiply it by itself. That takes one more operation. This is the second operation. But now, this is great because if I square that again, yes, you only do it 10 times. If you square it again, then you get 1, 1, 1, 0 to the power 8. And that's going to be just this matrix 1, 1, 1, 0, fourth, times 1, 1, 1, 0 to the fourth. And so that just takes me one more operation, multiply it by itself. Whatever was the yellow thing when I get the answer, multiply it by itself, third operation. And if you just do this all the way down, somebody already saw, it's if I want to go to the 1024, 1024 happens to be 2 to the power 10. So 10 squarings works. And so this is a way of saving a lot of work. If I wanted to know what is the 1025th Fibonacci number, then I just have to square this matrix 10 times. Of course, the numbers will be big, but they'll be big anyway, even if I was trying to do addition. Addition meaning get F3 and then get F4 and then get F5. Instead of doing 1024-ish operations, I only need 10 operations. And in fact, if I was doing a number which was like 2 to the power 30, 2 to the power 30 is approximately 1000 cubed. And I see. So Isabella, you are absolutely right. Any Fibonacci number, you can write it in binary. So that's the next thing I want to do to help to go and save this, to close this particular lesson. We can get any Fibonacci number by using binary. And so, by the way, this is the nice one. This is just called square a bunch of times. But what if I had something else? What if I wanted to know let's choose something maybe less pretty. F7. We could do F7. If I want to do F7, it still work? Well, okay, maybe F7 is not a good choice because 7 is too small. Let me just choose some other number which is relatively nice to play with. I'll call it 130. Okay? That might be too nice. Let's call it 131. F131. If I want to do F131, I could get it with this way, F131, F130, and indeed I do have a choice on whether or not I put the F131 as the second entry or the first entry. That's not an issue. However, what I have here is I would need to do 1110 times, remember it's going to be 10 because those were F1 and F0. Okay? I missed the power. The power is 130. Okay, now unfortunately that's not good, but fortunately somebody has helped me convert something to binary. So 131, I chose 131 because 128 is a power of 2. I have a bit of trouble seeing how many digits to put, so I'm just going to write down the powers of 2. These are the place values, 1, 2, 4, 8, 16, 32, 64, 128. Okay, and so now I can actually convert this into base 2. If I convert into base 2, 130 in base 2 will have a 1 there, a 1 there. The answer that was put there was, there was something else put in the chat. That's 131 in base 2. You could also have done it that way if you went with the 131 in the bottom and the 132 on top. It doesn't actually matter which one you choose. But the way that I happen to write it, I would put this way, and the rest are zeros. Now what's the significance of this? So this is equal to 130 in base 10. The significance of this is now I'm just going to use a letter instead of writing this matrix so many times with these powers. I'm now going to write box with an A to represent the matrix 1, 1, 1, 0. And actually, oftentimes when people are working with matrices, we always do write these capital letters. I'm just going to say, again, what I learned from that professor when I was in college was that, if you write the box around it, at least from a student point of view, like from my point of view when I was thinking about this stuff, it was more clear to me that that's not a number because there's a box around it. I mean, somehow it's got some size. Okay, but yes, so now I need to do some operations. How many operations? Well, I will need to get a to the power 128 times a to the power 2. That's all I need. So all I need to do is a to the 130. So I need to do a to the 130. And that's just equal to a to the 128 multiplied by a squared. But you see, you get a squared along the way anyway. So the point is, if you're trying to get a to the 128, how do you get a to the 128? Well, you figure out what is a to the 1. That's what you already had. Oops, I should put the power outside. If I want to get a to the power 1, that's just no operations. That's for free, given. And then I have to figure out a squared. And so that's one operation. And I'll do this a whole bunch of times, all the way to a to the power 128. And now I have to count. So how many is that? So one operation to get there, 2, 3, 4, 5, 6, 7. Yeah, that makes sense. 7. So this is the 7th operation. Does this make sense? So it's the 7th operation, I think. I hope I didn't make a mistake. I think it's okay. Yeah, a squared is 2 to the 2 is 2 to the power 1, and the 128 is 2 to the power 7. So the first operation, the 7th operation. But once you got all of these, you already have 128 and 2. So you already have a squared, and you already have a to the 128. So you just take one more operation to go and cram the two together. So if you cram the two together, this is the 8th operation. So now this shows you that you have an efficient way of even getting the 130th Fibonacci number. And so one of the things you can then say is, what's this complexity? How much effort does it take? How many computations do you need? Oh, is it a coincidence that we're looking for F7 and it's 7 operations? Let's see. Were we looking for F? I'll say the thing that is related, that's useful, the thing that's related that's useful is that somehow the power we're looking for here is around 2 to the power 7. It's basically that's as far as I'll need to go. I don't need to know what is the matrix A to the power 256 because that won't help me. I can't multiply any more things together. So effectively, I will only need to calculate up to here. I'll only need to calculate up to the biggest power of 2. That's before my number. Okay? So in that case, we now have a technique, we have a recipe that we can use to go and calculate any Fibonacci number. If n minus 1 was a cube, then you could do it that way, I guess. That's true. There are other ways that you could try to also reduce. I mean, maybe you could go and say, let's take a cube and then cube it a bunch of times. There could be more efficient ways. I will say that my goal here was actually just to show what we call an order of magnitude estimate. Because earlier I said, what if you have a billion? The billionth Fibonacci number. Will that take you about 1 billion steps? Eigenvalues have come up. So I'll say that I was pondering whether to put eigenvalues into this class. I might, by the time we get to the class number 3, I might actually do that. But right here, I will say I don't even need it. You said eigenvalues because there is an effective way to go and write down what is the power of a matrix. It uses something called eigenvalues. But what I'll add to that is, so that's what I was teaching. I taught that to my class. At Carnegie Mellon, I teach this stuff to college students, this particular way of doing recursions because I teach combinatorics. And at some point I told them, using the eigenvalues, I can get this Binet formula. The Binet formula, I'm going to write down something which is probably wrong, but I'm going to say that something on the top of my head, this is what I'm getting off the top of my head. This Binet formula is something like this, okay? It might not be exactly this. It's something like this. I could be off by 1, and I apologize if I am. Binet formula looks something like this. It's something like 1 over root 5 times root 5 plus 1. Oops, it's better to write 1 plus root 5. 1 plus root 5 over 2 to the power n minus 1 over root 5 times 1 minus root 5 over 2 to the power n. Am I off by 1? The easiest way to figure out if I'm off by 1, it might actually be okay. The reason it might actually be okay is because if I put in n equals 0, it is 0. So my hope is that this is right. If I'm wrong, I'm sorry. I apologize to everyone. This could be off by a little bit. But the formula that people said looks something like this. And the golden ratio is here, by the way. This is the golden ratio. You can prove this Binet formula by using what you just said called eigenvalues to simplify a to the power n. And in fact, that's one way to get the Binet formula. But my claim is that actually the Binet formula is not any more efficient for you to calculate than the power of the matrix. This is actually quite interesting. Because if you want to use the Binet formula and you want to do f a billion, you're back to taking a power. In fact, the power you're taking, the power you're taking has only these, it only has these like real numbers, normal numbers. But then again, this is only a 2 by 2 matrix. So every one of my operations that I'm doing up here, it's like every multiplication is at most, how many multiplications are involved when you do 2 by 2 times 2 by 2? Some number which is not growing, in the sense that every time I multiply 2 by 2, that is the Binet formula. Okay, thanks, Chris. Then maybe I did remember right. But somehow, when I'm multiplying 2 by 2 matrices, it's not like I have to do a billion calculations. It's like somehow 2, 3, it's on the order of 12. I'm sorry, I might be off by 1, but it's somehow like, it's less than 16, less than 15 operations that are involved in multiplying a 2 by 2 matrix. But if you look at what's going on down here, if I'm going to still take these powers, I'm not going to take this power by multiplying it one after the other a billion times. In fact, I would get this power also by using repeated squaring. So no matter what, you're going to use repeated squaring. No matter what the computer science order of magnitude, that's what Matthew mentioned, the order of magnitude is still what we call logarithmic in how big the n is. Logarithmic in the sense that the log base 2 of 128 is 7. That's actually what we were doing up here. And log is just saying, log base 2 of something is just saying 2 to the power what equals the number. So, 128 is 2 to the power 7. So the number of operations I had to do was on the order of about 7. And when you say on the order of, usually what you mean is up to a multiplicative factor of maybe 2 or 4. It's like as n gets bigger, the number of operations I do is like the log base 2 of n times some number, like at most times 10. But the exciting thing is, as n gets huge, like to a billion, you don't really care too much about multiplying log base 2 of a billion by 10. Log base 2 of a billion is 30. 30 times 10 is 300. That's nothing compared to a billion. So the claim is that this Binet formula actually is not that much more efficient if you just look at the order of magnitude, same order of magnitude. And furthermore, if you actually wanted to figure this out, you have a square root of 5. How in the world anyway would you deal with the square root of 5? It is not legal to say, well, the square root of 5 is some real number, which I happen to know to 50,000 digits. That's actually not correct. The square root of 5, if you wanted to use this Binet formula and figure it out for n equals 1 billion, it is not safe to just use the first 5 digits of square root of 5. You need to use a ton of digits. At that point, actually what you'd end up doing is you'd probably end up expanding all of these as linear combinations of rational numbers and square root of 5 times a rational number. If you can see what I mean, what I'm saying is that as you're calculating 1 plus root 5 over 2 to the power 6, to the power 8, to the power 16, it's always going to be of the form a plus b root 5, where a and b are both rational numbers. And so what ends up happening is you actually are still dealing with two numbers. So that's what we'll get. So the interesting thing is that this is a nice formula, but the matrix power already gets you almost all the way. And this question, Lee, thank you Mike, thanks for asking. The binary equivalence of 130 is just for explaining what the largest value of base 2 is. That was one of the components. The value of putting this in binary was to tell me if I want to get 130, I can make 130 by taking 128 plus 2. So the key is I need to know a to the power 130. I want to break a to the 130 in terms of multiplying some powers of a together, where the powers of a themselves are powers of 2. So the exponents need to be powers of 2 in order for me to have gotten them through this chain of repeated squaring. So the goal was, you just take your a, you square it, you square that, you square that. You get a to the power all of these powers of 2, and then later, because every number can be expressed in binary, you can go and pick out which of those to multiply together. And Fred asks, isn't there an issue of round-off error with Binet's formula, which you don't have with the matrix method? Exactly. So the point is that if you ever were to use a finite precision square root of 5, you'd be out of luck with the Binet formula. But at the same time, the way that you would do it, the way that Mathematica would do it, or Wolfram Alpha would do it, if you tell Mathematica or Wolfram Alpha to do this with a whole number for n, they will not use a rounded off version of root 5. They will be dragging around the answer as things like some rational number plus some other rational number times root 5. It's like how we have our students often submit their answers as the simplest radical form. We don't want them to give us a decimal. We often want them to say it's like, 3 plus 2 root 7 or something like that. And so what I'm saying is you're actually still dragging around some numbers, like there's a 3 and a 2 or whatever in front of the root 5. Okay, so this now finishes the discussion of the fact that with this particular matrix multiplication, because of the fact that matrix multiplication is associative, because of the fact that I can say I will first do all of what it takes to take the nth composition of this particular function, that's the power. Like, that's why we should care about these things. And actually, it's true. The reason why many people care about matrices in general is because they are linear transformations. I'll give a piece of advice. Some people sometimes ask, in this modern day, when there's this big data, when there are all these computer algorithms, what kind of math is going to be the most useful? A lot of high school students are often asking, what should they try to learn? I usually give the advice that linear algebra and matrices and understanding matrices are one of the most fundamental things that you will use if you ever want to use mathematics, say in the modern computer science and machine learning. And the reason is because it's very convenient to try to model things by linear approximations. Actually, we may have people here who teach calculus also. The entire notion of a derivative is a linear approximation to a function. And of course, if we want higher degree things, we can use the Taylor series. However, the idea is that a linear approximation is often very powerful. And what's going on in real life when you have this quote unquote big data, you have so much data that if you try to fit something which is not linear, you might what we call overfit, which is now going to give you something that matches the data. But when you try to use it to predict for anything else, it's like you're extrapolating beyond what data you have. So what I'll say is, this is the heart of statistics, linear algebra, these linear transformations, and even the idea of thinking of a matrix as what happens when I have some set of inputs, and I transform them linearly to get something else. My kids overfit all the time, says Seth. Yes, unfortunately, I also was one of those people before too, because I used to say, well, come on, you just like add more degrees of freedom in what you're going to fit, and then you're in good shape. But fortunately, as Bruce says, derivatives and integrals are linear. So actually, you just said something about derivatives and integrals being linear. The fact that those are linear operations is also very helpful. In fact, something I'm doing right now, some of you may know I'm actually also involved in trying to do something about the coronavirus. And one of the things that I was doing even just yesterday night was thinking about the linear transformations that are related to something called the Fourier transform. So Fourier transform is that all the sound waves that are in the world are often decomposable into sine waves of different frequencies. But it turns out that decomposition is a linear transformation in the sense that, well, I'm trying to invert a linear transformation, but it's a linear transformation because I could say the sound you're hearing in this split second is like three units of 440 hertz sine wave plus superimposed with 6 units of a 600 hertz sine wave, and so on. And so this entire idea of linear algebra and linear transformations and matrices is something that I was also using just last night. So to me, this is trying to give in this first lecture. Oh, physics talk, yes. So yes, I actually should say these days I've been thinking quite a lot about physics because of some of the work I'm doing. But the idea that all of these things break into linear is actually why the matrices come in. And so the goal of this first session, which we're wrapping up now, the goal of this first session was basically just to talk about that aspect, to say, you know, the way that I learned about matrices when I started was they are a shortcut for solving systems of equations. And that was the only understanding I had of them. I thought it was convenient, and there were some rules I would follow. I knew why the rules worked, because I knew they worked even without the x's, y's, and z's in systems of equations. But the first time I took a linear algebra class, I actually also was somewhat confused. I took a linear algebra class at a university, and suddenly it became very theoretical. And I didn't quite know what was going on, to be honest, because what is this linear thing, that linear thing, and so on. I happened to take that class twice. I went to a different place, and I took that class again at a university. Finally, I understood it. So to me, it was actually the second time in my life that I came across this sort of linear stuff, that I came to appreciate that the matrices and the linear transformations are the same thing. Finite dimensional linear transformations are the same thing. So my hope is that this first session helped to maybe demystify two important pieces, or maybe three important pieces. One is, why in the world is matrix multiplication defined this way? The second is, why is it associative? And the third is, what useful thing can I do with it? And so that will actually close out what I had prepared for this first session. We will have 2 more sessions of this, and those 2 more sessions will happen at the normal schedule of Math for America. My guess is that they're also going to run over this YouTube Live plus the Zoom conversation. What I will do now is I'm actually going to close off the YouTube Live to the world, but I will actually switch my conversation directly to the Zoom call with all of the teachers, just because I want to do a quick debrief directly with all of the teachers that we have instead of this one-to-many. So to anyone who was watching online, we really enjoyed having you here. For all the Math for America teachers, I'm going to switch to my video that's on the Zoom call. See you all next time.